All right, this section will be all about negative integer exponents. So far, we've only really kept our exponents to be positive numbers. Now, in this section, we will toggle between both and talk about if we have an exponent that is a negative number. And we're going to keep them as negative integers. You'll notice also negative integers, so negative whole numbers. We'll learn how to simplify these expressions using the negative exponent theorem, recognize different properties of still using the properties we've discussed, how do we use these with negative exponents, and then lastly, bring in some real world examples as well. We'll do that throughout. So starting with, we'll probably be taking a pretester in class. So if we could turn to this. Scientific notation is a perfect example of where you have seen negative numbers as exponents used before. So you definitely need to know what scientific notation is, powers of 10, and standard form. A standard form of a number would be its regular version, its decimal notation. So can you go from standard form of a number to scientific notation, or from scientific notation back to a standard form? So scientific notation, let's start there with a good definition. And these should be like warm-ups actually, because you've seen them before. So start thinking, what power combination? What is 28 times 10? Well, you know 28 times 10 is a number. And some of you would say, oh, that's the number. And did you get it right? Whoa. And did you get it right? It's 28 times 10, or 280. So most of you did the 280. So what's 28 times 10 to the second? Well, you know what 10 to the second is, so that times 28. So again, you're seeing a pattern here. And third one. So then I say, well, from that pattern that's established up there, not just your multiplication tables without a calculator, what would 28 times 10 to the 22nd be? So the pattern you established up there was when I multiplied by 10, which was 10 to the first, I had 1 0 on my answer. And then 28 times 10 to the second, I basically had the number 28, and I moved the decimal 2 places. Whoops, not the whole problem. I moved the decimal 2 places to the right. This one was 10 to the third, and I took the number 28, and I moved it 3 to the right. So we're saying, what would happen here? You should take the number 28 and move it 22 places to the right. Sets of 3, that would be 1, 2, 3, 4, 5, 6, 7 sets of 3, which is 21 with 1 extra 0, gives you 22 places to the right. So it'd be a huge number. But it's not the size that we're worried about. It is definitely the pattern. All right. With that, so can you describe the pattern? If we're just talking about powers of 10, which are perfect positive exponents, 10 to the first, 10 to the second, 10 to the third. Now, maybe I should have written it the other way and made the numbers go up as they went up, but what's happening here? As we increase a power every time, what's happening? Some people say you're adding a 0. No, we are multiplying by a power of 10. So as we go up, these numbers are getting multiplied by 10. So people say, look down. Well, if we go backwards in terms of exponents, we go down the scale, we would be dividing by 10. So you should know that your powers of 10 are nothing more than multiplication or division by a power of 10. All right, simple enough. You've seen those in scientific notation, so I think that's where we're headed next. Which one below is different and why? So start looking at these numbers. Again, we're looking for a pattern. 1.45 times 10 to the 5th. 6.3 times 10 to the 9th. 9.7393 times 10 to the negative 3rd. 14.8 times 10 to the 4th. And 6.30926 times 10 to the negative 7th. So looking at those, we all say they're a number times a power of 10. We have 2 of them that are negative powers, so that can't be the pattern. And we have 3 of them that are positive powers. What else do you notice? I think I've heard it, yes, that all of these are a single number decimal except that guy. So if you look, our definition of scientific notation was you must have only 1 digit, then a decimal, so the numbers 1 through 10, but not 10, a multiplication sign, and then the power of 10. So this one is not in scientific notation when all the others look like they were. So the 14.8 times 10 to the 4th was the odd man out because he's not in scientific notation. So a reminder that scientific notation definition says a number is in scientific notation. So that's what we're talking about here. Scientific notation. If it is written in the form a times 10 to the n, where a is a number between 1 and 10, but not 1 or 10. So it has to have that decimal look. And then n is an integer. And right now we're saying n can be a positive number, negative number, as our exponent. So look at all these down here. 3.4, it's a number between 1 and 10, times a power of 10 that is a positive number or a negative number. 5.43, a number between 1 and 10, times by a power of 10. 9 times 10 to the power of 10. So we're seeing lots of nice combinations that we've seen before. So scientific notation, definitely used and seen before. Here's a good real-world example from physical science. It says, write the number in scientific notation. The temperature at the sun's core is 1.55 times 10 to the 6th. So that number is in scientific notation, and I misspoke. It says write it in standard notation. So in order for you to do that, you're thinking, well, wait a minute. I have to take the original number, so 1.55, and if I'm multiplying it by a power of 10, and that's 6, that means I need to be able to move this 6, 1, 2, 3, 4, 5, 6 places to the right. When I do and come backwards and put my commas and things in place, we'll have a 1, 5, 5, 0, 0, 0, 0. Put your commas in. We have 1,550,000 as the temperature in kelvins at the core of the sun. Hot, 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 hot. Then it says the mass of the smallest insect, a parasite wasp. This is 4.92 times 10 to the 6th. So again, you would take your decimal that was given, move it based on your exponent 6 places to the right. Looks like we're going to move it 1, 2, 3, 4, 5, 6. Put your decimal point there. And again, bring your numbers back. Put in your commas appropriately after every 3 place values. So 4,920,000 grams mass of the smallest insect. And I think that took us to the picture of that. Don't know if it's going to, so let's try it here. So that smallest parasite, there it is. An example of that, the smallest one, smallest insect. Okay. All right, back to our slides. Use the function box below to convert numbers from scientific notation to standard form and remove them to change them back. So again, these are scientific notation, or supposedly. Are they a number between 1 and 10? Times by a power of 10 that could represent a positive or negative integer? They look like yes. So can you convert them? Do you know, if I just picked one at random, do you know what 5 times 10 to the 3rd turns into? Put it on your paper or in your brain. Give you 5, 4, 3, 2, 1. Is that the decimal you had on your paper? If not, look back at it again and ask yourself what happened. 5 times 10 to the negative third would be the 5. The decimal point has to move to the left because of the negative exponent this time. So in doing that, you would have had your 5, and you have to move this 3 places to the left. If our decimal's here, 1, 2, 3 puts it to the left, so our final answer 005, or 5/1000ths. Okay, that's what you're supposed to be able to do. Again, we can move these. Let's do another one. Let's take 4.7423 times 10 to the 8th. Write down on your paper what that would look like as a standard form number. Give you a second. 5, 4, 3, 2, 1. Is that your standard form number? 474,230,000. Bring it back if you have questions. This is one there's a positive exponent, so you should be bringing it to a positive 8 places to the right. You got to move it 1, 2, 3, 4 just to get it past the current digits that are in it, and then 4 more decimals. Add your commas. You should be good. Draw a line to match the question with the correct answer. So now here you have the answers right here. It should be easy. They're visible. Which ones go with which? You can see 6.83. Okay, so start thinking, where are your lines? Where are they matched up? Did you get 6.83 times 10 to the 8th up here? Did you get 6.83 times 10 to the 4th here? And the only one that got moved to the left, right there. Okay, check your work, check your thinking. Can you move from standard form to scientific notation? That's what we're practicing. Here's another example that will let you work out, and if you have questions on, you can bring to class. But here we have a body that contains about 3.2 times 10 to the 4th microliters of blood for each pound of body weight. Each microliter of blood contains about 5 times 10 to the 6th red blood cells. Find the approximate number of red blood cells in the body of a 125-pound person. So double check. I think we got our weight here. We're going to have to multiply that times the microliters of blood for each pound of body weight, and then that times the 5 times 10 to the 6th, which is for each microliter, blood contains that many blood cells. So you got 2 multiplications to do. Try it, and we can share that answer in class. And we want the answer in scientific notation. Now, when we actually do multiply scientific notation, the rule is not bad because we get to use some of our properties. So double check in case you haven't seen this before. So if we give you scientific notation, do not just punch it into your calculator. Especially, what if you don't have a calculator? The rule is take your decimals that are up front, whether they're leading whole numbers or decimals, multiply them together. We get a 0.8. And then the rule is 10 to the 5th times 10 to the negative 12th is a multiplication of like bases. So the rule is multiply by 10 to the, add the exponents. That would give you a negative 7. Right? And then if we want it in scientific notation, that now tells us, wait a minute, find our current decimal point, and we're going to have to move it 7 places to the left. 1, 2, 3, 4, 5, 6, 7. That would move our decimal point all the way down here. 1, 2, 3, 4, 5, 6, 7 leading zeros. Then our 8 should be our final answer in scientific notation. So now look at this pattern. We had already done the positive exponents, and I still have a couple of them here. So when I go from 10 to the 3rd down to 10 to the 2nd, 10 to the 1st, 10 to the 0, we knew when we went up this scale before that we were timesing by 10. So now when we go down the scale, we are dividing by 10. So when we got from 100 and we divided by 10, we got to 10. When we got from 10 and we divided by 10, that's how we got to 1. When we got from 1 and we divided by 10, that's how we got to 1/10. So double check, because some people always think 10 to the 0 power is 0. 10 to the 0 power, anything to the 0 power is 1, because at that point you will be dividing by a like term. 10 divided by 10 if we're in powers of 10. If we're in powers of 7s, 7 divided by 7, it'll always be 1. You'll be dividing by a like factor, which means you'll always get an answer of 1. And so these are not, notice, turning into negative numbers. They are just turning into smaller numbers. And notice, if we can bracket these off, that 10 to the first and 10 to the negative first, and 10 to the second and 10 to the negative second, and if I would have had a 10 to the third and a 10 to the negative third, there is a word we can use for all of those. 10 to the 0 is sitting pretty right in the middle, but all the rest of them, they're paired. And they're paired such that these are called reciprocals. Let me clean it off so you can see them again. If 10 to the first is 10, 10 to the negative first is its reciprocal. Well, the reciprocal of 10 means flip me, and the reciprocal of 10 would be 1/10. That's exactly what we got when we did 10 to the first. 10 to the third is 1,000. So when we do the reciprocal of that, we'd be thinking of 1/1000th. And that's exactly what you would have if we added that next negative exponent up here. So we are not getting negative answers, negative valued answers, if you want to say it that way. We are getting not getting negative numbers. We are getting smaller numbers than their counterparts. We're getting the reciprocal. So a negative number, couple of notes to take. A negative sign in the exponent does not make the expression negative, is what we just tried to say. And so if we give you b to the n and b to the negative n, they are called reciprocals. What else? If we said write 3 to the negative second as a fraction. So you're thinking, all right, let's see. That means 3, flip the reciprocal. So 1 over that number. So 1 over 3 to the second. And of course we know 3 to the second is better known as 9. So 1/9 would be that fraction that we're looking for. Write each equation without fractions. And if we do that, we should be able to, and we do have half and half here, so let's put that back up. Put that. So write each equation without fractions. So right now we have d equals k over w. So if we were doing work, if we were doing work to that, it would probably go something like this. How do we undo division? What would we multiply? So we would have d times w has to equal k. So write each equation without any fractions. That doesn't have any fractions. On this one we have a divide by d cubed, so we again would have to times by d cubed on both sides. And so no fractions. So that's one way to do it. Some people will also say, well, can I do like example here, can I take and write it as a reciprocal? Sure, we could have d equals k times w to the negative first. That would put it up top. On this one, we would have had n equals k times d to the negative third. So two different looks. Do we want positive exponents? Then we'd have to have dw equals k. d cubed times n equals k. If we want negative exponents involved, the circled answers would be the best choice. All right, last but not least, let's go ahead and simplify with our rules now, and then we'll try 1 through 18 together. Here it looks like we have division, and the rule was like bases, subtract the exponents. So 5 take away 8. You must subtract in the order that's present, numerator minus the denominator. So 5 minus 8 is a negative 3. If the directions say no negative exponents, then we would have to do the reciprocal look, and we would write y equals x to the third. And the next one. Like bases, subtract the exponent. So face value, we'd get y equals 2 minus 7, negative 5. Reciprocal, 1 over y to the fifth. Okay, on this one, simplify. There's really nothing to do. However, if that direction says no negative exponents can exist, because that's pretty typical, we don't like negative, then we're thinking reciprocal me, and if I'm 1 over x to the negative third, the reciprocal would be x to the third over 1, if you like, better known as just x to the third. So that's how we need to take care of our negative exponents as well. Use the same rules we did for multiplying, dividing with the negative exponents, and we'll bring those into play as we move forward, even in the next couple sections. So you have enough to go with, new information about negative exponents. Any questions, bring those to class, especially about scientific notation.